We are back. Jeez, was that frustrating. I knew immediately that I lost the connection because it was buffering on the screen and I constantly look at the screen. So, let's wait for people to come back in. I'll wait till we have 24. And we did lose 30 minutes of class. Let's see how we progress for today. And the backup is always the fact that you have videos to watch for this class. But there are certain things I want to do. I want to make sure we cover for today. I think we'll have enough time before 12 o'clock. So let's just wait a moment for the others. I'll recap. It's pretty self-explanatory. Where we left off. Let's wait for 20 to come. So the first part is recorded, and I'm just adding a second video onto the playlist. Okay? And I have to do that because otherwise I might lose elements. I might lose the chat or I might lose the captions because of the break in the connection. That tends to happen. Okay. The others. As I said, we should be fine. I sent an email to everyone with the new details. And keep in mind that I don't have to set you a link to every class. You can just go into the playlist and you'll find the current class. And then broadcasting. Can everyone hear me? I shouldn't lose internet again. That was very strange. Probably should reset the router each morning or each day before class, just to be sure. Let me see if I have to reconnect them. Oh no, looks like it's connected. It's still connected. All right, I just need to know that you can hear me so I can continue. Can you hear me? It's back volume. Very strange. Why would that be? Let me have a listen. I did. It's my AirPods. It's my AirPods. Let me see if I need to reconnect them. Oh, okay. No, they were not connected. Okay, how's that? They're not connected. That's what I have to do. Very strange. Too many details here. I'm not sure. It's not recognizing that. Oh, maybe I have to press this. So bad. I think that frozen. Very strange. It's coming. There you go. Now, how is this? Is that better? Now I'm connected. It looks like everything disconnected. Okay, I'm back. Yeah. Thanks for your help. The problem is I have an older computer and I ordered a new one. It's just taking forever to arrive. Very good. Very good. All right, so let's see how much we can do. I'm sure we're going to be fine for the time. I'm sorry I'm wasting your time with the technical issues. If we lose contact again, I'll just have to do the same thing, but I don't suspect we will lose connection. All right, so we are 23. Very good. Let's continue, right? Let's just continue. Remembering that you can find the streams in the playlist for MBAUNDHLive. All right. So this is the spending data. These are dollars spent by customers, and I mentioned these are in numerical order, but not necessarily order of arrival or departure of customers. Okay. And the question I ask regarding this data were, how much do shoppers spend in the store, and how can the data help improve the store's marketing strategy? So again, I'm going to use a similar, the systematic approach I developed for solving these sorts of problems. Problems with data and data reporting. Okay, reporting, summarizing statistics, summarizing patterns, and then summarizing statistics. The next data set is this one. This is data that was collected over 100 years ago when Simon Newcomb measured the time in seconds that light signal took to travel 7.4 kilometers from his lab to a mirror at the base of the Washington Monument. And his goal was to measure the speed of light. So the speed of light should be some sort of constant, but in fact, it turns out there is a little variation in the speed of light. So there's other things that interfere with its speed.
So he used this method to get this data in the data set. So this is Newcomb's data here. Now these numbers are very small deviations from the general value. Okay, so these are just nanoseconds, where the general value was 24,800. The measures in the data are deviations from this. Okay, so some of the measures were smaller and some were greater, but only slightly. Okay, so nanoseconds are already very instantaneous, very brief. And adding just a portion on, we're going to look at the variation to show that it's not exactly constant, but there is slight variation in the values, and we want to summarize those. And the final data set is information on hot dogs, different types of hot dogs. There's meat, poultry, and beef hot dogs. And the question is going to be, are there any systematic differences among the three types of hot dogs in terms of calories? Because there's going to be different data that you're given information on in terms of calories. So that data looks like this one here. So this is the beef and poultry. So meat, hot dogs, poultry hot dogs, and beef hot dogs. And this is the weight of the hot dog. Okay, so this is the information for the fourth data set. This one here, these are, because again, just like I did with the spending data, I presented the values in numerical order, but not order of observation. Also in the Newcomb data, I presented the data in numerical order, but not in order of observation. Here we have the order of observation for Newcomb's data. I wonder if that's accurate. So actually, if I go down, where's the first observation? Apologies. Okay, so the point is that these are the data sets related to these questions, okay? So I'm going to begin. I actually want to start with the spending data. So now I'm going to ask you to move from this document to the Unit 2 GDS document. Okay, so these sample problems are problems that I present and then I solve them for you in this document that you see called sample problems. But in general, we're going to use the lecture notes for Unit 2. So let's take those. So once you have data, like the list that I demonstrated to you, what you want to do is summarize. All those numbers revealing the patterns that are regular and the irregular or anomalies that occur in the data. You begin by demonstrating the distribution of the variable according to the data. You want to show this is what a distribution is. Now I write it like this sometimes, but that means the same thing. What it demonstrates are the values the variable takes and how often it takes these values. You always begin with a graphical representation of the data, and depending on the graph that you get, you can compute statistics from these samples. Okay, that's going to be the approach. For categorical variables, like the ones we discussed on the first day of class, you'll use frequency distribution tables and graphs such as bar charts and pie charts and something called Pareto diagrams to demonstrate or to summarize those distributions. But for continuous variables, where we're going to focus, because that's much more challenging, we use stem and leaf displays, histograms, and box plots. I'm not going to talk about MBAUNDHLive much. These are different kinds of graphs to display distributions. If you have two variables and you're trying to demonstrate the relationship of two variables, you'd use cross tables, time series plots, or scatter plots, and we'll talk about those as well. Okay, so these are the different kinds of graphs. So let's start with the stem and leaf graph, and let's use the spending data. So let me know that you have this document that you're you know where I am? Okay, so confirm with me that you have this document. Let me know in the chat. I do not know why that is displaying. What is happening? What is happening? What do you guys see on your display right now? You should be seeing not sure. There you go. Not sure what happened. Again. All right. So you made a comment Is it a rule of thumb to use the mentioned graphs for categorical variables and continuous variables? Yes, that's the convention. So it's a convention to use these kinds of displays or graphs for categorical and these type for continuous. And when you have two variables, so these are for univariate, we call univariate statistics. That's like one variable at a time. And then for two variable statistics, this is what you do. Okay. So make sure everybody has the okay, so everyone has this data set, no one's commenting. Okay, so you have this data set. And here we have the 50 shoppers and what they spent. Okay, so you have 50 shoppers and I put them in columns for ease of calculation. And what I generate here is called the stem and leaf plot of the spending data. Can you tell me what I've done to generate this plot? And then we're going to look at it, analyze it. How did I generate this plot? What I'm going to do is I am going to bring this data down so you can see it. Look neat. I can take this down here. Okay, so that's the data alongside the stem and leaf plot. And we see now the data has been put in order. So that's an important thing is to realize the difference between ranked or ordered data and order of observation. So this is already ranked. It might, however, be important also to retain information of the order of observation. Okay? You'll see that when we talk about the other data set. So you see number 2 here. This person spent the least. They spent $2.32. That appears in the stem and leaf plot here. What's been done to generate the stem and leaf plot? Oops. Oh, I'm not going to be able to move this now. I need that to be out of the way, but okay, it's fine. I can work with this. So what's been done is the data have been grouped into common terms. Remember, a distribution shows the values and the frequency of those values appearing in the data set. So what has been done is that classes, what we call classes, or intervals, are determined for the data. So let's start with the numbers 0, 0, because someone could have gone into the store and spent $0. So 0, 0 to 0, 4 is the first interval. So anyone spending between 0 and $4 will fall into this class. The next class goes from $5 to $9 and so on. Okay, and I'm going to explain this, but I want to show you first how this is done. So these are mutually exclusive. Data can only fall into one class, not more than one. Any comments? Okay, so I've done all of this using the dollars, but what happened to the cents? In fact, rounding was used to eliminate or round up where this 661 becomes $7 and this becomes $2. Let me do that a little clearer. I will use, so this becomes $2, this becomes $7, this becomes $7, and so on. So all the numbers have been rounded and then assigned to their class. Let me add that 2 is then seen as 0.2 in the stem and leaf plot, and 7 is seen as 0.7. And the reason why I have 2 digits is because the last number is 69. So because all numbers in the stem and leaf plot have to have the same number of digits, that should sound familiar. It's the approach that we used in labeling. Since 69 is the last one, and it has 2 digits, all the numbers should have 2 digits. Questions about rounding and eliminating the decimals? So first we rank the values, then we round, and finally we assign them to classes. So the first value, 0.2, has the first digit that's a 0 and the second digit that's a 2. The first digit is called the stem, like the stem of a plant, and the second digit is the leaf, the leaves of the stalk of a plant. Because a plant can have one stem and many leaves, you see what happens. It's a grouping in classes of common numbers. So you can reveal a pattern separate from all the details and the noise that appears in the original data. So the second observation is 0.7. So the first stem is 0 and the value is 7, that's a leaf. The subsequent one is also a 7, so you see it appears here, 7, 0, 7. The next one is 8, so it's 0, 8. The first digit is also 0, and the second one is 8, and then 0, 9. So all of these go here. So the interval of the classes are of equal length, and it includes 5 numbers in each. So 0 to 4 is 5 separate numbers, 5 to 9 are 5 separate numbers, and so on. But numbers may be repeated in the original data. So as we had 2 7s, we had 2 7s, and then 8 9. The next values go in the next class. And you see we have all of these fall in this class. Any questions? So we rank the data first. We round the values to eliminate detail in this case. We create classes and then assign the data to the different classes. Notice the way the classes are determined, the first digit has to be the same for all the values in the class. See, so they can share the stem. So 10 to 14 includes 10, 11, 12, 13, and 14. Now 15 to 19 includes 15, 16, 17, 18, 19, and it explains why I don't use the traditional 15 to 20 category, right? I need to use that one in the subsequent one, where the stems are the same for all values in the class. So that's how you draw what's called a split stem and leaf plot. It's split because I work between classes of 5 as opposed to a conventional 0 to 10. Okay, it goes by class. Classes go by 10. Okay, so I'll repeat. Let's repeat. Okay, should I erase this and repeat? Let's see. What I'll do is I'll do it on another page, okay? Let me take this. No, I can't do that. Okay, let me take this. So if people want me to repeat, I will repeat. However, you could watch the video. This is important to cover. So it's not a multiple of 4. There's actually 5 values in here. It's 0. So this contains 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. So it's actually 5 values can fall in there. Okay. I have to clean this up a bit before I take it away. Like watching me do this? This is why I'm using this system. Okay, so let's repeat. Okay, ready? Everyone paying attention? All right, so these are the original data here. And looking at the data, all I want, the goal is to display the distribution, which shows the values and the number of times they appear. So what we do is we divide the data into groups of common numbers. So we create classes. And notice the stem, it runs through the number line, but in groups of 5. The values 0, 0 through 0, 4 fall in the first class. In the second class, values 0, 5 to 0, 9 will fall. And then we begin 10 to 14. And the reason that this is done is so that all the values that fall in this class have the same first digit. So the values that fall into this class are 0, 0, 0, 1, 0, 2, 0, 3, and 0, 4. That's a total of 5 different numbers. So each interval is of length 5. So you get the idea, I hope. So that is true for this interval as well, this class. Every digit has the same first value that falls into here, and the second value is called a leaf. So the stem is the same for all of the values in this interval, and the leaf can vary. The values that fall into that second class are 0, 5, 0, 6, 0, 7, 0, 8, 0, 9. So the first digit goes, that's common to all of them, falls here under the stem column, and the rest go here. So where are these numbers coming from? They're coming from the rounded value. We round the decimals and change these values so that the first one becomes $2, the second one becomes $7, the third is 7, the fourth is 8, the fifth is, and so on. Oh, that one's 15. So I'm just showing you those ones for now. It's 5 in each interval. 1, 2, 3, 4, 5. And this one has 1, 2, 3, 4, 5. It has to be equal size. So now, to represent this number, every single value needs to have the same label. So the last one at the bottom is 69. So there's a range of values from 232 to 69 something. Let's see what it was. 69.49. Okay, so those are the range. That's the range of values. So since the last one has to have a label of size 2, I need to make to fit onto this stem and leaf plot. That's why I have 2 digits, because the last one has to have 2. And this becomes 0.2, this one becomes 0.7, this one becomes 0.7, 0.8, 0.9, and then we start 10, 11, 12, 13, 13, 14, 14, and 14. And the first group, just the 2 alone, appears here. The 7, 8, and 9 appear here. And the 10, 11, 12, 13, 13, 14, 14, 14 appear here, and so on. Okay, so that's how we make it. And so there's different ways you can draw this graph. In this class, because it's just a beginner intro class, I'll give you instructions how to make it. In reality, though, and we will discuss this, you can make all different kinds of variations of this graph. I went by size 5 classes. You could go by size 10. You could go by size 2. You could do whatever you like. The goal, however, whatever you make, the goal is to reveal the pattern of the data and irregularities in the data. Okay, that is the goal, the objective. I'm not sure how to, this has to go. I gotta erase that one. Okay. All right, so the goal is, following the instruction I provide, or you get a graph like this, so you see it's created going by 5. I'm going to erase this to clear my, you know what, I'm going to just do another, I'm going to make another. So most of you, I hope, understand how it's created. If not, we can talk about it later because we do need to move on. This is the stem and leaf plot. So what we can do with this we can see what it does, creates a distribution. I can move it on its side like this as well. Okay, so I can look at it vertically or I can look at it horizontally. This is the number line underneath, and it shows the pattern of the data. It demonstrates. Now I can smooth out this distribution. I can do it like this. If I believe that there are three distinct groups of data or customers. So if I believe these are unique customers and these are their purchasing patterns, I see three groups. Maybe you don't see three. Maybe you just see two groups. Or maybe you see just one big group and then just a few out there. Let's not even make it a hump. Let's just say there's some extreme values out there. I'm not even going to give it too much attention. So these are three what I call idealized these are density curves or idealized notions of the data. And it's based on what you know about the population and what you see in the data. So do you think there's three groups that are purchasing in the store? Maybe, okay, so these customers are spending the least, but they're the largest group. These customers are spending the most, but they're the smallest group. And these are in between. So it's important to recognize different groups because for targeting marketing, you want to know who your shopper is, right? What is the profile of shoppers in your store? Maybe these customers here who are spending $60 to $70, these shoppers, maybe they're not even residential customers, maybe they're businesses and they're buying larger quantities relative to the customer who's coming in to just buy one or two items. Okay? So if you believe there's three groups, then you would use the red idealized version. So what the idealized density curve implies is if I had more data, if I had all the data, I believe if I had all the data, so if I had all of the observations in the population, I believe this would be the pattern. There would still be three groups of shoppers. If you're in the green, what you believe is that there's just two groups. That if I had more information or more grocery shopping data, this would just be one group of people who spend less than the second group who spend a lot. Clearly, if you had all of the data, this would be a higher peak, but the pattern is what I'm interested in, not the height so much, the pattern, the relative pattern of spending. If you go with the blue distribution, you think there's fairly just a few extreme shoppers out here spending a lot relative to everybody else, okay? So students don't like to have to make decisions when they're just learning. So I'm not going to expect you to make those decisions. I'm just showing you the possibilities, all right? And I'm going to stick with the first one. I'm going to, in my summary, I'm going to stick with the version that there's 3 groups. And I'm going to stick with, I'm going to summarize the data based on those 3 groups. Questions? So I'm just going to continue. You can review the video and let me know if you have any questions. And I will use timestamps to help direct you so you can find this part of the video easily. But I'm going to proceed with the 3 groups. So what are we going to say? What we need now that we have the graph that we've selected, I'm going to clean this up. I need to clean this up. Yes. Clean. Oh, I can do this easier, but I'm scared of losing the graph. All right. All right, so we have settled on this shape, 3 groups of shoppers, and that is my graphical representation. Now, based on the graph, we are ready now to summarize the data. And then, after we summarize the data, we will answer the questions. There are 2 questions, actually, with this data set. First, I need to tell you about how we're going to do this. The systematic approach that I mentioned involves identifying the 5 features of a distribution. Okay, now to demonstrate those 5 features, I'm going to use the baseball data, okay, and then we'll return to this data if we have time. But have no fear. You have videos to describe most of this topic. You'll see all the pages of this unit are covered in the videos that I've already edited. And I've linked on the platform. So let's go to the Maris and Ruth data, and then we'll come back to here. Where am I going to get it from? Let's see. I'm going to go back to the document here, and we're going to use this information. Oops. So you guys can take a 5-minute break while I set up for this discussion of the 5 features. I'm going to ask you to take 5 minutes. I actually need to get some water myself. Okay, so take a 5-minute break while I set things up. Okay, that's even. Even to me. Okay, so what we need to do next, everybody there? What we need to do next, okay, this is our data set for Maris and Ruth. Maris data has one, two, three, four, 5, 6, 7, 8, 9, 10 observations. The sample size is 10. So this is the sample size where it was decided that the sample of the Major League games each season was appropriate. Okay, so then with Ruth, her sample size, or his sample size is, let me move this over a bit. Sample size is 15. Okay. What we want to do is create a graph where we can observe the data in a comparative way. So we want to compare this data to this data. We're going to use the stem and leaf plot. So we're going to go by 10. And we're going to place them on back to back on the same stem. And I'll show you how to do that. First, what's the first step? What do we need to do as a first step to creating a stem and leaf plot with this data? The first step is to rank order the data. So we begin with the Maris, and I'm going to put these numbers in order. The first value is 8. The next value is 13, followed by 14, followed by 16, and then we have 23, 28, no, 26, 28, and 33, 39, and 61. So those are the ranked values. And let's do the same thing for Ruth. So this will be a little more difficult because there's more numbers. So let's see. The smallest value is 22. Next is 25. Okay, I'm going to stop and see if you need any help. You see what I'm doing? We don't have any issue of decimals here. These are whole numbers. So we can just proceed. So 25, the next one is no more 20s. Let's start with 34. 35. Now no more 30s. We're in the 40s. We have 2 41s. And then we get into 2 46s. 3 46s. And then 147. 54. 2 of those. Oh wait, 49. 2 54s. A 59 and a 60. So that's the data in order. Yes, Patrick will do for each of them. And now, let's create a back-to-back stem and leaf plot. let's place in the middle the stem, where the range of values, the smallest is an 8, and the largest is a 61, right? So we're going to start with 0. Let me make a point about the classes. So it's going to be 0 here. The class will be 0, 0 to 0, 9. Now I'm going to use the stem and leaf, which goes by 10. So then the next one goes 10 to 19, and then 20 to 29, and 30, 39, and 40 to 49, 50, 59, and 60 to 69. I'm going to make you have to make the bottom visible. See that? Okay, so I'm going to erase I have to erase the classes. I'm going to move them. I need to move this out of the way. Move it over there. Because what I really want to do is put the data here. So we're going to have the leaf on this side for Maris. And the leaf on this side for Ruth. Now what you need to do is complete the stem and leaf. Now if you've drawn this on your own side, could you finish it and then I will show you the answer? Of what you think it will be. Use your intuition. Ask me questions if you're not clear. How's it going? So what you're going to do is the values for Maris will go here. So anything between 0 and 9 will go here. So we're going to put a 9 here for Maris. And then 13, 14, and 16. So they have to be in columns, right? You want to keep the column orderly. The next one is 23, which would be 2 and 3 makes 23, 26, and then 28. The next is 33 and 39, and then nothing, and just a 1 out here. So that's for Maris. So there's gap. There's a gap here. For Ruth, we start with 22, so we start all the way up here. And I'm going to, the number line usually goes from left to right, but in a back-to-back stem and leaf plot, I will include the numbers going right to left, okay? So it's a mirror. This is like a mirror. So this is, I'm going to put it here, like a mirror. Well, it's not a mirror because it's not the same thing, so I shouldn't say that, should I? It's exactly a mirror, but the number line is mirrored. So that's 22, 25, and then jumping to 34, 35, 41, 41, 46, 46, 46, 47, 49, and that's that. Then 54, 54, 59, and a single 60. Oh, I put a 09. Yes, 08, thank you. I don't know why I put 9. Correction. Let me fix that. Sorry for confusion. Let me know if I made any more mistakes. I don't know why I put 9. Okay, this is not perfectly, but it should be approximately, straight in the column. Maybe I can fix this one a bit. All right, so this is a smaller pair of data sets, but you can do the same analysis that we did before. What I want you to do is make the idealized density curve over the data, implying what you think the data would look like if you had more observations. So let's say we included all of the home run hits over their career, not just the ones in the major league games, because this is just a sample from major league games. So what do you think it would look like? So I'll draw mine after I give you more opportunity to draw yours. Let me know if I made any more mistakes. So we didn't have to do anything fancy. We didn't have to round values. We didn't have to make a split stem and leaf. The only thing that I asked you to do here was make them, the stem and leaf, back to back. So that's the new thing that we've done here. All right, I'm going to draw my density curve. I think the curve will go like that. And here the curve will go like that. Now, statistics is about averages or expected values and relative measures. Okay, now when we look at data sets together, I can compare them in their pattern. In this case, I would describe Ruth's distribution as peaked and reliable. It's a tight distribution. Whereas Maris's distribution is flat. Now you might say there's a peak here, but it's relatively speaking, it's very flat. So these are the observations we make. At the outset. Notice the way that we've done this, I've grouped together common numbers. So even though Maris got 61 and held the record for a decade or so, Maris had a long-standing record and got 60 home run hits, and they both, in my drawing, just fall in the same class anyway. So they're seen as high numbers, the highest of all the data, but it looks like Maris's peak Ruth's peak is above most of Maris's data. So that's another observation that I make. So I'm going to add that in. Well, let's say, hold on, let me correct that. I'll just say higher than Maris. Okay, so it's higher than Maris. The peak is above almost all of Maris's data. That's really relevant. That's really important. Okay, so that's our observation. Now, based on our observation, now what we're going to do is complete the 5 features. We're going to review the 5 features, systematically reporting. Now, it looks like I cannot move this for some reason. Nope, cannot move this. So what I'm going to do is take this drawing with me to another page. Okay, copy. So what we're going to do is list the 5 features. The first feature is the shape, and I'm going to comment on the shape for Ruth and the shape for Maris. The second feature is dependent on the first. So let's start with that. How do we describe the shape? Now, I've said it in a few words here. I've used descriptive words regarding the shape of the distribution. But in one word, how would we summarize this distribution? Does anybody know? When you have a distribution where the peak is at the center of the data, such that what's on one side is mirrored on the other side. Now, it's not precise, remember. What I'm looking at is the blue shape that I've drawn. Okay, so I believe, by making the blue shape, I believe if there was more data, I think it would have this pattern. This would just fill in here, and this would just be a smooth, what we call, yes, okay, so it's, we could call it symmetric. Symmetric is the word, and I guess a bell curve, yes, because there's only one peak. So let's use the word, the keyword is symmetric for what I want to do. In contrast, Maris is not symmetric, but I want a precise word, very precise about its shape. And what is the word I'm going to use? Does anybody know? Not asymmetric or non-symmetric. The word that we use is English, is skewed. What would it be in French? I do not know. I should look that up. Right, skewed. And particularly, to be precise, there is an extreme observation relative to the other values on the right of the number line. So if I was to turn this on its side, this would appear to be a skewed value on the right. Because there's an extreme value here on the right tail. Okay, so we call it right skewed. So the skewness regards the extreme value, the single outlying value. Yes, it's exactly comments from Kinold. It's skewed as like a bias. It's just a unusual, anomalous case, and it requires investigation, which we're going to discuss. Okay, so we have a symmetric and regular pattern distribution versus a skewed, flat, irregular distribution with a extreme value, unusual or anomalous or curious extreme value. Now, that's what we're going to say about the shape. The shape informs the statistics that we will use. Keep in mind, these are continuous discrete data, right? So the next feature is known as the center of the distribution. Another word for that is expected value. Remembering that statistics has the goal of alleviating uncertainty, what would you choose as the expected value if you were to travel in a time machine and be a betting person and bet on the home runs in a season that Babe Ruth would get? What range of values would you bet on? Which class would you expect his home run hits to fall in? In an average year, you would expect him to get 40 to 50 or 40 to 49 hits, right? Because that's where the peak is. That's what the peak tells you, the most likely observation. So the center is a reflection of what you expect. It will do the same for Maris. Where would you expect? What's the expected value for Maris's home run hits? It's less precise, right?